Hello everyone, and welcome to this video. Today, we're going to understand how generative AI works, especially ChatGPT. Now, what does generative AI actually mean? Simply put, it refers to AI systems that can create new content instead of just analyzing or sorting existing data. For example, they can write text, answer questions, create stories, and even write computer code. In this video, we'll take things step by step. We'll start with the basic ideas and then gently move into slightly deeper concepts so everything feels clear, simple, and intuitive. Let's begin. Before ChatGPT can exist, it has to go through something called the AI or machine learning life cycle. Don't worry, let's break this down one step at a time. First comes data collection. This means gathering a huge amount of text data. Books, articles, websites, research papers, and documents so the AI can learn how humans actually use language. Next is data preprocessing. Here, the data is cleaned and refined. Duplicate content is removed, broken sentences are fixed, and unnecessary symbols and noise are filtered out, so the AI learns from high-quality information. After that comes feature representation. Now, computers don't understand words the way humans do, so text is converted into numbers. This numerical form allows machines to process and understand language. Then we move to model building. This is where the AI's brain is designed, how information flows inside the system, and how decisions are made. Next is training. During training, the model makes predictions, checks where it went wrong, learns from its mistakes, and gradually gets better over time. After training comes evaluation. Here, engineers test the model to see how accurate it is, how safe it is, and how reliable it is in real-world situations. And finally, we have deployment. This means the model is released for real users while being continuously monitored and improved. ChatGPT follows all of these steps, but on an extremely large scale. Now let's understand the step-by-step process behind building a generative text AI model like ChatGPT. We'll go through this slowly and make each step easy to understand. Step 1. Data collection. Everything starts with data collection. In this step, a massive amount of text data is gathered from different sources like books, articles, websites, social media, and online documents. This collected text becomes the training data. Just like humans learn a language by reading and listening, AI learns language by analyzing huge amounts of text. And remember, the more diverse and high quality the data is, the better the model learns. Step 2. Data cleansing. Once the data is collected, it goes through data cleansing, also known as pre-processing. Here, the text is cleaned and standardized so machines can learn from it more easily. This includes things like removing unnecessary special characters, converting text to lowercase, handling punctuation properly, and removing noise or inconsistencies. The goal is simple: to make the text clean, consistent, and meaningful before training begins. Step 3. Tokenization. Next comes tokenization. Tokenization means breaking text into small pieces called tokens. A token can be a full word, part of a word, or sometimes even a single character. So instead of treating a full sentence as one big unit, the model breaks it into smaller parts that are easier to process. Tokenization helps the model handle new or unknown words, learn language patterns more efficiently, and work with text in a structured way. Step 4. Embeddings and positional encoding. After tokenization, these tokens are converted into embeddings. An embedding is a numerical representation of a token. In simple terms, it converts words into numbers in such a way that similar words have similar values. Embeddings help the model understand the meaning of words, similarity between words, and contextual relationships. Along with embeddings, positional encoding is added. This helps the model understand word order. For example, the difference between dog bites man and man bites dog. This step allows the model to understand both meaning and position of words. Step 6. Transformer architecture. Now we reach the core intelligence, the transformer model. A transformer is a special type of neural network designed specifically for language tasks. In fact, GPT stands for Generative Pre-trained Transformer. Transformers work by predicting the next token based on previous tokens, using a mechanism called attention. Attention allows the model to focus on important words, understand context, and capture long-range relationships in a sentence. Before transformers, older models like RNNs and LSTMs were used. But after 2017, transformers proved to be faster, more accurate, and more scalable. Step 7. Training the model. Next comes training. Training means teaching the model to make better and better predictions. The model learns by predicting the next token in a sentence, comparing it with the actual token, and measuring the error using something called a loss function. A loss function simply tells the model how wrong it is. To improve, the model adjusts its internal values, called parameters. You can think of parameters as the model's memory. They store what the model has learned. This improvement process uses backpropagation, where errors are sent backward through the network to improve future predictions. Training happens in batches and is repeated millions of times until the model becomes highly accurate. Step 7. Inference, text generation. Once training is complete, the model enters the inference stage. Inference means using the trained model to generate new text. When you give ChatGPT a prompt, the model predicts the next token, adds it to the sequence, and repeats this process one token at a time. This continues until a stopping condition is met, like the end of a sentence or a complete response. And this is how ChatGPT generates human-like text in real time. So from raw text data to intelligent, meaningful responses, all these steps together power a generative text AI model like ChatGPT. Now, let's take a quick look at the recent history of generative AI. First, let's clarify one thing. The word generative simply means the ability to generate or create new content, like text, images, audio, and even video. And here's an important point. Generative AI is not a new concept. For example, Google Translate, which launched way back in 2006, has been using generative techniques since its early days. Even Google Search Autocomplete, the suggestions you see while typing, uses ideas from generative AI. So if this technology has been around for so long, the big question is, what has changed recently? The answer is scale, capability, and accessibility. In January 2023, ChatGPT gained 100 million users in just 2 months, one of the fastest adoption rates for any technology in history. Then came GPT-4, which claimed performance better than 90% of humans on the SAT exam, a standardized test widely used for college admissions in the United States. And for the first time, regular people, not just researchers, could ask an AI to write essays, poems, computer code, jokes, and much more, all in simple, natural language. This sudden jump in capability and ease of use grabbed the attention of common users, developers, and industry experts alike. And that's why generative AI feels like a revolution today, even though the idea itself has been around for years. Now, let's see how quickly different platforms reached 100 million users, starting from the right side. At the extreme right, we have ChatGPT. ChatGPT reached 100 million users in just about 2 months. This makes it one of the fastest adopted consumer technologies in history. Its instant usefulness, global availability, and AI-powered capabilities drove massive adoption. Just next to it is TikTok, which reached 100 million users in around 9 months.
Short-form videos, a powerful recommendation algorithm, and highly engaging content help TikTok grow at an unprecedented speed. Moving left, we see Instagram. Instagram reached 100 million users in about 2.5 years. Its mobile-first design and visual storytelling made it extremely popular, especially among younger users. Next is WhatsApp, which achieved 100 million users in approximately 3.5 years. Free messaging, simplicity, and cross-platform support helped WhatsApp scale globally. Then comes Dropbox, which took around 4 years to reach the same milestone. Its simple cloud storage solution and referral-based growth strategy played a key role. Next is Facebook, which reached 100 million users in roughly 4.5 years. Strong network effects made Facebook grow faster as more users joined the platform. Moving further left, we have Twitter, which crossed 100 million users in about 5 years. Real-time updates and public conversations fueled its adoption. After that is Airbnb, reaching 100 million users in roughly 8 years. As a two-sided marketplace, its growth depended on both hosts and travelers joining the platform. Next comes Netflix, which took about 10 years to reach 100 million users. Netflix had to build content libraries, streaming infrastructure, and consumer trust over time. And finally, at the far left, we have Spotify. Spotify took around 11 years to reach 100 million users, growing steadily through licensed music content and gradual global expansion. This progression clearly shows how technology adoption has accelerated over time, with AI-driven platforms now spreading faster than ever before. Now let's understand how the generative AI process actually begins. The very first step is building a vocabulary. A vocabulary is simply a list of text units called tokens that the model understands. Before the model is trained, all the text data goes through a pre-processing stage. Pre-processing means cleaning the text, removing noise, and preparing it so the model can learn efficiently. One popular technique used to build this vocabulary is called Byte Pair Encoding, or BPE. Byte pair encoding works by breaking text into small pieces and then repeatedly merging the most frequently occurring pairs of characters or tokens. These merge rules are saved in a file often called vocab.bpe. Once created, this vocabulary file is stored along with other model files and reused during both training and text generation. Now, a real-world example. GPT-3 uses byte pair encoding for tokenization, and its vocabulary contains around 96,000 tokens. A token here does not always mean a full word. It could be a part of a word or even a single character. On the other hand, Google uses a different algorithm called WordPiece, which is used in models like BERT and Gemini. Now let's understand tokenization with a simple example. Imagine we have a small text corpus like low, lower, lowest. This is just a simulation, not the actual tokens used by GPT. Initially, the vocabulary starts with individual characters like L, O, W, E, R, S, and T. Next, the system counts how often each character appears. Then it looks for the most frequently occurring pairs of characters that appear next to each other. For example, L and O frequently appear together. O and W appear together. E and R appear together. So instead of treating them separately, the algorithm merges them into new tokens like low, O, ST. This process repeats again and again, gradually building larger and more meaningful tokens. Over time, the vocabulary evolves from single characters to meaningful word parts. On the right side, you can see how a simplified vocabulary looks. Each token is assigned a number called an index. For example, the might be token 1, cat token 2, sat token 3. You'll also notice special tokens, such as UNC for unknown words, BOS for beginning of a sentence, EOS for end of a sentence, PAD for padding shorter sentences. These special tokens help the model understand sentence boundaries and structure. So, in summary, byte pair encoding allows the model to handle new and rare words, reduce vocabulary size, learn language patterns efficiently. This vocabulary building step is the foundation on which the entire generative AI model is built. Now let's move to one of the most important ideas in modern AI: embeddings. Every word or token in the vocabulary does not stay as plain text. Instead, each token goes through an embedding process, which converts it into numbers that a machine can actually understand. An embedding is simply a multidimensional vector. That means a long list of numbers. You can think of this like giving every word a numerical fingerprint. In the image, you can see examples like man, woman, king, and queen. Each of these words is represented as a row of numbers. Now, look at the labels above those numbers. Things like living being, human, gender, royalty, verb, plural. These are called features. A feature is just one aspect of meaning. Each number in the vector tells us how strongly a word relates to that feature. For example, the word king scores high on human and royalty, while woman scores high on human and gender. Important note here, this is only a simplified simulation. Real models don't use human-readable labels like royalty or gender. They use abstract dimensions that the model learns on its own. But the idea remains the same. All these numbers together form a point in a high-dimensional space. On the right side of the image, you can see this idea visualized. Words like man, woman, king, and queen appear as dots in space, and the distance between them represents meaning. Words with similar meanings appear closer together. Now, here's where it gets really interesting. Because these are numbers, we can do math on meaning. That's why this famous example works. King minus man plus woman equals queen. This doesn't mean the model understands gender or royalty like humans do. It means the mathematical relationships between vectors align in a meaningful way. Now let's connect this to large language models. The slide mentions that GPT-3 uses embeddings with 12,288 dimensions. That means every single word or token is represented using 12,288 numbers. Each of those numbers captures a tiny piece of meaning. Together, they form a very rich and detailed representation of language. These embeddings are usually stored in vector databases, which allow fast searching based on similarity, like finding words, sentences, or documents that are semantically close to each other. So when you ask ChatGPT a question, it's not just matching words, it's comparing meaning in this high-dimensional space. That's why it can understand context, synonyms, and even analogies. In simple terms, words become numbers, numbers capture meaning, meaning becomes math, and that math is what powers modern AI. Now let's talk about neural networks, which form the core of how models like ChatGPT actually learn. The idea of a neural network is inspired by the human brain. On the left side, you can see an image of a biological neuron, where signals travel from one neuron to another through connections called synapses. Artificial neural networks, or ANNs, are a simplified mathematical version of this idea. In an ANN, we have artificial neurons, also called nodes. Each neuron by itself is very simple. It performs a small calculation and then applies something called an activation function. An activation function decides whether the neuron should pass information forward or not. A very common activation function used today is called ReLU, which simply means if the value is positive, pass it forward. If it's negative, ignore it. The real power of a neural network does not come from one neuron. It comes from millions or billions of neurons connected together. Now, look at the diagram on the right. The data first enters through the input layer. This could be text, an image, or numbers, converted into a numerical form the network can understand. Next, the data flows through multiple hidden layers. These layers are called hidden because we don't directly see what they're learning, But this is where the real intelligence happens. Each connection between neurons has a weight. A weight is simply a number that tells the network how important a particular input is. You could think of weights as stored knowledge. The network combines inputs with weights, applies activation functions, and passes the result forward layer by layer. Finally, we reach the output layer, where the network produces a prediction. In this example, the output is a probability, like dog, 0.9, cat, zero point 0.1, rat, zero point 0. This means the network is 90% confident the image is a dog. Now, how does a network actually learn? This happens through a process called backpropagation. Backpropagation works like this. First, the network makes a prediction, then it compares that prediction with the correct answer and calculates an error. That error is then sent backward through the network layer by layer. Based on this error, the weights are slightly adjusted so that the next prediction becomes better. This cycle, predict, measure error, adjust weights, happens millions or billions of times during training. Over time, the network becomes extremely good at recognizing patterns. Now, to connect this to large language models, the largest version of GPT-3 has 96 hidden layers, built using stacked transformer decoder blocks, and around 175 billion parameters. A parameter is simply a value the model learns, mostly weights and biases. More parameters mean more capacity to store patterns and knowledge. So when you talk to ChatGPT, you are interacting with a massive neural network that has learned language patterns from enormous amounts of data using these exact principles. In short, individual neurons are simple. Intelligence emerges from large-scale connections, and learning happens through backpropagation. This is the foundation of modern AI.
Now let's go a little deeper and understand how transformers actually work. For humans, understanding language is almost effortless. When we hear a sentence, we immediately grasp meaning, context, and intent. But for computers, language is extremely difficult. Computers don't naturally understand words or ideas. What they are very good at, however, is working with numbers. And that gap between human language understanding and numerical computation is what this slide is showing. In the sensor, you see a simple example, the word apple. As humans, we instantly understand that apple could mean a fruit, or it could refer to a technology company. The meaning depends entirely on context. That kind of contextual understanding is easy for humans, but very hard for traditional computer programs. Older language models tried to process text word by word in sequence, which made it difficult to understand long-range relationships in sentences. This problem was fundamentally solved in 2017 by a research paper from Google titled "Attention is All You Need." This paper introduced a new architecture called the transformer. The key idea behind transformers is something called self-attention. Let's explain that simply. Attention means deciding what to focus on. Self-attention means each word in a sentence looks at other words in the same sentence to understand its own meaning. So instead of reading text strictly left to right, a transformer looks at the entire sentence at once. For example, in a sentence like, "I bought an apple because it's a good idea to invest," the word apple pays more attention to words like invest and good idea, and less attention to words like bought. That's how the model understands that apple here refers to a company, not a fruit. Mathematically, this works beautifully because transformers convert words into numbers and attention becomes a weighted calculation over those numbers. That's why on the right side of the slide, you see the idea that computers struggle with language but excel at numbers. Transformers bridge this gap by turning language into numbers without losing context. This self-attention mechanism is the foundation of modern models like GPT, BERT, and Gemini. If you want to see a visual, step-by-step explanation of how transformers work internally, the Illustrated Transformer article by Jay Alamar is an excellent reference.
And for those interested in the original research, the Attention is All You Need paper is still one of the most influential AI papers ever written. So, in summary, humans understand language naturally, computers understand numbers, transformers convert language into numbers while preserving meaning through attention. And that is the core idea behind how ChatGPT understands what you type. Now, let's talk about an important trend in modern AI. Bigger models generally perform better. This slide shows that idea using two perspectives. One is the number of neural connections, and the other is the amount of data used to train the model. Let's start with the chart on the left. This graph shows the number of neuron connections per model over time. In simple terms, these connections, also called parameters, are the adjustable values inside a neural network. They're what the model learns during training. More parameters means more capacity to store patterns, more ability to model complex relationships in language. On this timeline, we move from GPT-1 to BERT, then GPT-2, T5, GPT-3, Palm, and finally GPT-4. You'll notice the numbers growing exponentially. GPT-1 had around 100 million parameters. GPT-2 jumped dramatically to about 175 billion parameters. And GPT-4 is shown approaching the trillion parameter scale. The chart even compares these numbers to biological systems. At the bottom, you see references like ant brain and rat brain, and near the top, the human brain, which is estimated to have around 100 trillion neural connections. While AI models are still far from the human brain in structure and capability, this comparison helps us visualize how rapidly model complexity is growing. Now let's look at the chart on the right. This graph shows the number of words processed during training. Language models don't learn from experience like humans do. They learn by reading massive amounts of text. For example, GPT-1 was trained on tens of billions of words. GPT-2 and GPT-3 scaled into the hundreds of billions. Palm and GPT-4 moved into the trillion word range. The green line at the top represents all human written text, while the red line at the bottom shows how much text a human reads in their entire lifetime. This contrast is important. A single large language model may process thousands of times more text than a human ever could. GPT-3 was trained on roughly 45 terabytes of data. That's not just Wikipedia. It includes books, articles, websites, code, and more. Finally, the visual at the bottom uses bubble sizes to represent model scale. You can clearly see how models like GPT-3, Palm, and GPT-4 grow larger over time, reinforcing the message. As model size increases, so does capability. Of course, bigger is not always automatically better. It also requires better training techniques, better data, and better alignment. But historically, this scaling trend, more parameters plus more beta, has been a major driver behind the rapid improvements we see in models like ChatGPT today. So, to wrap it all up, ChatGPT may look like magic, but it's really a well-designed pipeline of ideas. Language is first turned into tokens, then into numbers using embeddings. Those numbers flow through massive neural networks trained using backpropagation. At the core is the transformer, which uses self-attention to understand context, deciding what matters and what doesn't in a sentence. And as models get bigger and are trained on more data, their ability to generate meaningful language improves. ChatGPT doesn't think like a human, it predicts intelligently. And that combination of data, math, and scale is what powers modern AI.